Welcome back to the Drawing Board by TBPi. This week we're going to be talking about half-life and catalysis. A lot of people think of half-life as just being a concept that deals with radioactive decay, but really it can be used for just about any chemical reaction. Half-life is the time it takes to consume half of your starting reactants. So essentially it is the time required for your concentration of reactant A to be equal to 1/2 of the initial concentration of A. Now, it's also important to remember that half-life is basically just you keep cutting the amount of starting reactants in half. So you can have more than one half-life. So after your first half-life, you are down to 50% of where you started. After your second half-life, you're down to 25% of where you started, and so on and so on. So one of the types of questions that you can be asked is, okay, let's say we have a target percentage of reactant that we want to get to. You may be asked to find out how many half-lives that will require. Now the formula for this is pretty simple. It's 1/2n, where n is your number of half-lives, is equal to your target percentage. So for example, if we want to know how many half-lives it takes to reach, let's say 6.25% of our initial amount of reactants, then we say that 1/2n is equal to 0.0625, and then we solve for n. This is some pretty simple algebra. Just make sure you don't forget your log rules because they become pretty important when you're doing math like this. So we can rearrange this to be 2n is equal to 1/0.0625, which just so happens to be equal to 16. Take the natural log of both sides. So the natural log of 2n is equal to the natural log of 16. Using your log rules, you can pull this n down front. So n times the natural log of 2 is equal to the natural log of 16, and n is equal to the natural log of 16 divided by the natural log of 2, which when you plug that into your calculator is 4. Now you might be thinking to yourself, well, hey, I can calculate in my head pretty easily that 2 to the 4th is 16, but the calculations aren't always going to be this simple. This works out nicely because 6.25% is a whole half-life quantity, but let's say we wanted to reach a different percentage. If our target percentage is 2%, you'll see that the numbers don't come out quite as nicely. So same exact process, 2n is equal to 1/0.02, and that's equal to 50. It's not immediately obvious what n needs to be to make your final answer 50. So again, we'll walk through this same process. We'll just skip to this step. We'll say n times the natural log of 2 is equal to the natural log of 50, and n is equal to the natural log of 50 divided by the natural log of 2. This comes out to 5.6 half-lives. So now you may be wondering, wait a minute, if half-life has to do with time, then how are we supposed to calculate the time required for a half-life? To figure this out, we're gonna have to backtrack a little bit and talk about integrated rate laws. So integrated rate laws are exactly what they sound like. They're just the integrated form of the rate laws that we've talked about before. So for example, for a 0th order reaction, where your rate is just a constant regardless of the concentration of your starting compounds. If you were to integrate this from your initial to final concentration, then your integrated rate law becomes your concentration of your compound A at a given time t is equal to your initial concentration of A minus K times T. And you can see why this would be useful. Knowing your instantaneous rate doesn't necessarily tell you anything about the concentration at that point. Keep in mind, this is for a reaction A goes to B, just to have the simplest possible example. And you can repeat this process of integrating for first and second order reactions. So for first order, where your rate is defined as your concentration times your constant, integrating this equation, and I'm not going to walk you through the algebra because it gets a little bit more complicated. All that you really need to know is that the natural log of your concentration of A at a given time t minus the natural log of your initial concentration of A is going to be equal to negative kT for a first order reaction. For a second order, the same process, but now your rate is Ca squared times your reaction constant. And the integrated rate law for second order reactions is 1/, your concentration of A at time t is going to be equal to K times T plus 1/, your initial concentration of A. Now again, you can see why these integrated rate laws are going to be really important for half-life, because half-life cares about the relationship between your concentration at a given time and your initial concentration. Remember that a half-life is the time required for Ca of T to be equal to 1/2 of the initial amount, the initial concentration of Ca. Now that we have the integrated rate laws, it's pretty easy to see how we can use them to determine the time required per half-life. All you need to do is plug in 1/2 of CaO in place of Ca at time t. So this is your 0th order half-life time. As long as you know the values of K and CaO, you can really easily solve this equation for T. And you can repeat this process like we did earlier with the other integrated rate laws, just plugging in 1/2 of CaO in place of Ca of T, and then rearranging to solve for T. So now that we know our integrated rate laws, let's do an example with a half-life calculation. So we have an A to B reaction that is first order with a given K value and a given CaO. Well, since it's first order, we know that we can jump straight to our integrated rate law, that is the natural log of the concentration of A at given time t minus the natural log of CaO is equal to negative kT. Because we're trying to find the half-life, we can immediately replace Ca of T with 1/2 CaO. Now, remember your log rules, because taking the difference here means that we can rewrite this entire side of the equation as the natural log of 1/2 CaO divided by CaO is equal to negative kT. This is the only case where this happens, but for all first order reaction half-lives, your initial concentration actually doesn't matter. This will always cancel. What we're left with then is the natural log of 1/2 is equal to negative kT. We know the value of K, it's given right here, so this is equal to negative 3.71 times 10 to the negative second t. Notice that because K is in per second, the final t we calculate here will be in seconds. When you plug and chug for t equals 18.70 seconds. You can imagine that the time required to reach a half-life can vary pretty substantially depending on your K. For a really slow reaction, the time required to use up half of your reactants would be really, really high, whereas for a super fast reaction, the time required is going to be really low. Using the exact same conditions, let's do this calculation again, but make it second order this time. So same exact K value, although the units are going to be different because reaction constants need to have units that will make your rate come out correctly in your rate equation. And if you try and use a K with a unit of per seconds in a second order reaction rate equation, it's not going to work very well. But the process here is exactly the same. We'll start with our second order integrated rate law, which is 1 over the concentration of A at a given time t is equal to our rate constant K times t plus 1 over CaO. Again, our first step is to replace our Ca of t with 1/2 CaO. So this becomes 2 over CaO is equal to 3.71 times 10 to the negative second times t plus 1 over 3 molar. And I could have written 3 mole over here as well. Same deal, nice and easy, plug and chug. We can subtract our 1/3 across, so we're left with 1/3 is equal to 3.71 times 10 to the negative second times t. When you plug and chug, t comes out to be 8.98 seconds. And it makes sense that this t would be faster than our first order reaction with the same exact conditions. Let's take a second to look back at our integrated rate laws, because these can be really useful tools for determining the reaction order of a reaction where you may not know its order. Looking at the format of these equations, you can see how, depending on what you choose to plot, whether or not that plot is linear, it can be a really good indication of which order you have. Zero order is probably the easiest to think about, because this equation is already in the form y equals mx plus b. If you plot your concentration of A as a function of t, then your y-intercept will be CaO and your slope will be K. Things get a little trickier when you start looking at your first and second order. For first order, if you were to move this term to the other side of the equation and you were to plot the natural log of your concentration as a function of time, then the natural log of your initial concentration will be your y-intercept, and again, K will be your slope. Second order, you don't need to move anything around, but you're plotting the inverse of your concentration versus time. Again, K is your slope, and this time your intercept is 1 over CaO. So if you're doing experiments in the lab and you don't know the order of your reaction, you can start by plotting your concentration versus time, and if that plot alone is linear, you have a zero order reaction. If that's not linear, you can then try plotting the natural log of your concentration versus time. If that plot is linear, you have a first order reaction, and again with your second order reaction, reaction, if you plot the inverse of your concentration versus time, if this plot is linear, you then have a second order reaction. So switching gears a little bit, let's talk about catalysis, which is another facet of kinetics that usually doesn't get the attention it deserves. The general mechanism that catalysts use to speed up reactions is to form some kind of intermediate with your reactants that can then form the products with a lot less energy than without the catalyst. You can think of this in terms of your Gibbs free energy. So if we have a plot of your Gibbs, normally you have some starting point and you have to get over this activation energy hump before you can come to your products, this activation energy gap here. If for some reason this activation energy gap is too large, you can use a catalyst to try and lower the required activation energy. So instead of following this high hump path, you follow some shallower path to get to the same product. In some cases, the reaction that you're trying to catalyze won't proceed at all without the help of the catalyst, because it's impossible to have enough energy to get to the final product without a catalyst. In most cases, however, the reaction can proceed without the catalyst. It's just an extremely slow process. Another important note about catalysts is that they are not actually consumed by the reaction. So if we have some reaction, A plus B goes to make C, and you need a catalyst to make it possible for A and B to react with each other, your final product, there will also be some catalyst here, there will also be some catalyst here. Which is why typically when you see reactions like this, instead of bothering to write that you have catalyst on both sides, the reaction will simply be written as A plus B with your catalyst written over the arrow gives C. And this can be a nice reminder that, oh, right, my catalyst is not being consumed by this reaction. There are a lot of reactions of catalytic processes, but we'll just talk about a few for the sake of example here. So one example is CH2 double bonded to CH2 plus 1/2 O2 will go to make this really funky looking organic structure. This reaction is catalyzed by silver. Now, typically the way that metal catalysts work is that your reactants will come and they will bind to the surface of the metal. So let's say we have our silver surface here. This compound is going to come wander down and bind to the surface, as is our oxygen. And then once they're on the surface, they will find each other, react to form this compound, and then this compound will detach itself from the surface. That mechanism for metal catalysts is pretty common, and especially if you're a chemical engineering student, you're going to see a lot of this when you get into your reactor engineering classes. Another example a lot of people think about is starch hydrolysis. Starch hydrolysis is basically just the breaking down of more complex carbohydrates into smaller building blocks. So if we start with maltose, which is basically just two glucose molecules stuck to each other, and you add water, this will break down to give you two glucose molecules. However, just dissolving maltose in water, this reaction will happen, but it is incredibly slow. Even if you are boiling your solution, this reaction takes a very long time. But you can add an enzyme to this called glucoamylase. And the glucoamylase will bind to the maltose to form an intermediate that reacts very quickly with water to produce glucose. Now, if you've taken any amount of biology, you might know that something ACE usually indicates that it's an enzyme. And yes, this catalyst is in fact an enzyme. An easy way to think about enzymes is just as being biological catalysts. They're usually derived from some kind of biological process, and they're very important to many, many biological processes. I hope this overview of half-life integrated rate laws and catalysis was helpful. See you next time.